A very good afternoon to all of you. Today we are talking about hyperspectral remote sensing for urban areas. Till now we have seen that hyperspectral can be used for various dimensions using the high resolution spectral resolution imageries. Now we know that what hyperspectral remote sensing is. It has various contiguous bands and the spectral dimension of the image is very good in case of hyperspectral remote sensing. Let us see how it can be used in urban areas. Now, what is the need of hyperspectral remote sensing in urban areas? We all know that urban areas are made up of the natural targets and the man-made targets. The natural targets like the water bodies, the natural terrain of the green spaces. However, the man-made targets are the building blocks. Now, how building blocks are different? They are made up of different chemical compositions, and hence with the help of hyperspectral remote sensing we can distinguish these different chemical compositions. With the help of HRS data, it improves the quality of the surface reflectance, helps in identifying the chemical and the physical property of the materials. Because of the chemical constituent of the materials present within the urban canopy, it offers the potential of mapping the urban land use land cover with great precision and more quality. As I already mentioned, it is made up of the natural targets and the man-made targets, hence it becomes more complex to differentiate between these targets within the urban morphology. What are the important points that we have to remember using hyperspectral remote sensing in the urban areas? We need to know that the SWIR and the TIR are the most important combination of bands within the wavelength bands for the urban applications. One more important point that we have to understand is that the urban morphology is made up of the two dimension and the third dimension is also added to the urban areas. Hence, if we use a fused data or an integrated data of a high resolution 3D data to the existing 2D data, it will be of great help. What are the different applications of hyperspectral remote sensing within the urban canopy? It can be used for precise urban land use land cover mapping. It can be used for roof type composition mapping. As we know that in India, the roof can be made up of different materials. It can be made with tiles, it can be made with concrete, it can be made with cement and red tiles. So all these type of roofs can be differentiated with the help of hyperspectral remote sensing. It can also be helpful in differentiating between the different road types and the condition of the road. It is a newly constructed road or it is an old road, it is a tar construction, etc. Urban tree can also be monitored using hyperspectral remote sensing. As we know that in an urban canopy, the urban green spaces are reducing day by day due to urbanization. So it can also be monitored with the help of hyperspectral remote sensing. Urban heat island effect consequent to the urban tree monitoring can also be monitored. Urban flash flood can also be monitored. The oil contaminated soil and plastic material can be monitored. And the 3D data can be fused with the hyperspectral data for better classification results. One by one we will deal with two separate case studies. One that deals with understanding the anatomy of the urban areas using the Hyperion 30-meter resolution for the Dehradun case study area and using ICONOS and ALI data. ALI data has 9 bands. In this case study, we came out with a conclusion that SWIR, blue and NIR are best for urban mapping and for various urban features like brick, concrete roof, road surfaces, sand and urban bare soil. The different points or the different reflectance points can be marked in the wavelength spectra. This study reveals that for brick, concrete roof, road surface, bare soil and sand, what is the suitable spectral configuration. The second case study is the integration of the 3D data with the existing high spectral resolution hyperspectral data. Interestingly, in this case study, we have used an open source portal for downloading the high spectral and spatial resolution hyperspectral data, that is HRS. We have also used LiDAR data in a combination with the existing hyperspectral data for improved results. We all know that LiDAR has the third dimension and it can be fruitful, and how it is fruitful we will see in the later slide. As all pre-processing conditions for hyperspectral remote sensing, the before and after flash correction spectra is mentioned in this slide. As you can see that after the atmospheric correction, the spectra of vegetation is enhanced and is close to reality. Two approaches were identified. Number one was the SAM classification, that is spectral angle mapping classification. As you can see that 4 classes were identified, namely roads, buildings, grass and trees, and we can see that the achievable accuracy was only 73.4%. Now we come to knowledge-based classification. What is knowledge-based classification? Based on certain rules, we classify the image, and here we have used the third dimension of the LiDAR data, that is height as an input. What are the other variables that we have used? We have used NDVI, that is normalized difference vegetation index. We have used NDBI, that is normalized difference built up index, and NDSM, that is the normalized DSM, digital surface model. Aster spectral library was used for classification. We have not collected the spectra since the image is of San Diego in USA. In knowledge-based classification, we have divided into roads, buildings, grass and trees, and when we did the accuracy assessment, the achieved accuracy was 85%. If we can see in the right hand side the decision tree for knowledge-based classification, we can see that for buildings, roads, trees and grass, certain rules were made. For buildings, if the height is more than 1.5 meters and the NDBI is greater than -0.5, then it can be classified into buildings. Similarly, for all the other classes, the rules were made and hence the classification was performed, giving a better accuracy than the SAM classification. This slide represents the comparison of SAM and knowledge-based classification. The first image shows the image, that is the HRS image. The second is the SAM classification, and third is the knowledge-based classification. Below we have the classification results in zoomed image, and we can see that the knowledge-based classification has given the best results. We can also extract roads using this approach. So if we see on the left hand side, SAM classification has given us poor results since it has over-classified certain other pixels into roads. However, in knowledge-based classification, we have been able to extract the road in a better form. In conclusion, we can say that LiDAR and knowledge-based classification, the rules that are applied, can improve the urban classification to a large extent. It removes shadows between buildings from the preliminary classified image, and the overall classification accuracy can be improved to a larger extent. So this will be all for hyperspectral remote sensing for urban areas. At last, if a picture is worth 1,000 words, a hyperspectral image is worth 1,000 pictures. Thank you.